All right, to round out this last day of lectures, we're going to look at extending our calorimetry experiments to being able to determine how much heat is released when we do chemical reactions. And so we are going to do very similar types of experiments where we'll do a reaction within a calorimeter and we'll measure the initial and final temperature changes. So let's look at this neutralization reaction. We're going to take hydrochloric acid, solution of it, and a solution of sodium hydroxide, mix them together to neutralize, and that's going to generate some heat. Now we can do some stoichiometry to figure out how much products we're going to get, but we also like to know how much heat will be released. And in order to figure that out, we're going to use calorimetry, right? Which means that if we're doing a problem with this, then our formula will look something like this. The reaction will release heat, Q of the reaction, and the water that the reaction is done in will gain that heat. So here's our problem. We're going to take 100 milliliters of 1 molar HCl and mix it with 100 milliliters of 1 molar NaOH. They're going to completely neutralize each other. And if both solutions start at the same temperature, 21 degrees, once they're mixed together in a calorimeter, it reaches 27.9 degrees. So what is the approximate amount of heat released by the reaction? And then it tells you the density of the total solution is about a gram per milliliter. And then there's the specific heat capacity of water. So what we are going to find here is how much heat was released by the reaction. And we know we can use the heat gained by water to figure that out. So we're going to solve for the Q of reaction. And so we need the mass of the water, specific heat capacity of water, and the change in temperature of water. Now, what's kind of confusing is we're never given any masses here, but we are told that we should assume the density is 1 gram per milliliter, and we have 100 milliliters of one solution and 100 milliliters of another solution. So we have a total of 200 milliliters, and we're going to assume the density is 1 gram per milliliter. And so we have 200 grams of the solution. So let's plug that in here. 200 grams. Notice I'm kind of keeping track of sig figs here. The specific heat capacity is 4.184 joules per gram per degree Celsius. And our change in temperature is, well, the final was 27.9 degrees Celsius minus 21.0 degrees Celsius. All right, so notice here, I'm going to start canceling out some units. Grams cancel out, degrees Celsius cancel out, and I'm just left with joules. That's the unit of heat. That means I probably have set this up correctly. And then I do all of this math, plug it in the calculator, keep track of sig figs, and that comes out to about 5,800 joules. Notice the sign there. The sign's important. I'll explain why in a second. Or if we want to put this in kilojoules just to make it a little bit easier to read, that's negative 5.8 kilojoules. Now the sign is important. Okay? Don't just ignore the sign because a negative value, a negative Q means that the reaction released heat into the water. I'm going to kind of preview where we're going to be going next. When a reaction releases heat, that's called an exothermic reaction. And as I said, that'll be coming up later. You don't need to know that right now, but this is why the sign is important. A negative sign when we're dealing with these heats, a negative sign means that the substance released heat or the reaction released heat. A positive sign means that a substance absorbed the heat or the reaction absorbed the heat. And we'll kind of pick up with that whole negative and positive thing in our next series of lectures.